pressure because we have to upgrade at the same time. But for dike can upgrade every 10 years. So we are now considering how many options we have for different type of the infrastructure, and what kind of option can be available until certain level of the climate change. Because we want to know the limit of the adaptation depend on the target, depend on the method. So now we are trying to list up of all the possible adaptation measure, engineering measure for different coast, different style of the coast or at port and so on. Then some adaptation option is cheap and possible to upgrade every 10 years. That is good. The dike, cost, at least cost should be dramatically decreased. So you can keep same dike, but adding some nature-based solution, changing climate, that can be one option. And then additionally, mangrove growth will be faster under the changing climate because carbon dioxide in the air will be increased. So plants can be growth faster than now. That's a good point. So cost benefit and option is very important. So I'm happy to discuss next following year with Balai Teknik Pantai. Terima kasih.
Thank you, Professor Mori. I think we come to the time now. So thank you again, Professor Mori. Let's give a big round of applause for Professor Mori.
Terima kasih banyak.
Thank you. And we move to our second and third speakers. They are a team, actually. Their last name is the same. They're the same. So, Dr. Eva Yamamoto and Dr. Kodai, is correct? Am I correct? Right? Kodai Yamamoto. And they are going to present, talk about, the title is Applicability of Rainfall Runoff Inundation Model for Water-Related Disasters. So, Eva and received her doctoral degree from the Kyoto University. And for Kodai Yamamoto, bachelor, master's, and PhD from the Kyoto University. So probably that's the introduction. Please, the time is yours.
Thank you very much for this opportunity. Good afternoon. Selamat sore. Semuanya bahasa Inggris aja deh Pak. Presentasinya bahasa Inggris. My name is Eva Yamamoto. I'm from Innovative Disaster Prevention Technology and Policy Research Laboratory. And Pak Kodai Yamamoto is from Meteorological and Hydrological Risk Information Laboratory. And we both are from the same institution as Mori Sensei from Disaster Prevention Research Institute of Kyoto University. And today we are going to share our experience in the applicability of rainfall runoff inundation model for water-related disaster. Before I start, may I know if any of the audience have experience in hydrological modeling or have a background in hydrology? Okay, glad to know because in presentation I used some of hydrological terms that some of you may not know if you are not familiar with hydrology. So, so in today's presentation, first I'm going to explain our laboratory and also our research in the humid tropical region and little bit explanation on the model, rainfall runoff inundation model, and how it is applicable in this humid tropical region, and little bit I will share a little bit of experience in the studies on climate change impact. This presentation may be quite far to what Mori Sensei has explained, because the study is in inland flooding. So, and also we try to understand in this humid tropical region, since we don't really understand the process. So we try to be able to understand how to represent the process, the real process in the field into the model, so that we can have a proper modeling results. So, so our laboratory is called Innovative Disaster Prevention Technology and Policy Research Laboratory, and the head is Professor Takahiro Sayama. He's the developer of rainfall runoff inundation model. And together with Professor Sayama, there is also Lorna Sensei. She is French. Her expertise in anthropology, and myself, and Pakoda Yamamoto is also belong to our lab, but he is formerly belong to Meteorological and Hydrological Risk Information Laboratory, and we have another researcher called Sugawara Sang. But most of us, except Florence Sensei, most of us are doing RRI modeling. So this is just explanation of what we do in our laboratory. So we basically do we want to understand the connection between how to advance in technology and how to improve the policy in water-related disasters, including floods, droughts, and fire. And we have different projects. This is just as far as I know. So we have one in Japan, another one in Cambodia and Indonesia, and also in Pakistan. And we have a lot of projects. And the one that mentioned by Mori Sensei is SATREP's Indonesia BRIC. And also we have also Justi project, and also Sentang project is the one that is mentioned by Mori Sensei, also is the studies on climate change projection. So we are trying to do research in most of this area. And for Indonesian sites, we have several project sites. So one is, we started our observation site in nearby Kerinci Mountain in Jambi province. It's called Kancing Observation Site. Previously, it was part of Justi project, and then with the launch of the SATREP's Indonesian BRIC, we have another project in Bali and East Kalimantan, the new capital city. And under the Sentang project, we are trying to focus on the impact of climate change in tropical peatland, particularly the one in Sumatra and in Kalimantan. So this is under the Justi project. Just briefly explain that. So we are trying to assess the impact of climate change on hydrology, including the vulnerable pit swamp areas located in the coastal areas of Sumatra. And we try to understand the process by monitoring site at a plot scale. And then we try to make a hydrological simulation in the basin scale. And then we, for a climate change study, we try to use the climate change projection region and downscale, dynamically downscaled into this Batanghari River Basin by MRI. And we try to understand the process at the basin scale, so that we can he developed a flood hazard map at the basin scale and finally discusses sustainable adaptation strategies with stakeholders using the future projection. And part of the Sentang project, particularly emphasized for climate change projection, we are trying to understand the occurrences of floods and fire, and particularly happened in the coastal parts of Sumatra and Kalimantan. Maybe little have realized that actually in this part of Indonesia, floods and fire reoccurrence from year to year, and the frequency is getting higher from year to year, and we are trying to understand how to finally make an wise adaptation strategy considering the future climate. So the next slide will be explained by Hodai Sensei. Please.
Two time. So yeah, let me introduce the rainfall runoff inundation model. It's one of the physical model, also mentioned by Bori Sensei as one of the application of climate change to flood and storm surge. Yeah, so to understand how climate change impact to floods, since we don't know how rainfall changes in the future, we use a model output from climate model under the scenario. And then to understand how rainfall impacts on the floods, we are using this hydrological model. And this is called, in short, RRI model. It's open source. You can download from the website by the Civil Engineering Research Institute in Japan called ICHAM. So I'm not sure many of them are familiar with our hydrological model, but this is basically physical model. And this model can be run with rainfall input and elevation input. Land cover are the optional, but you can reflect it. And you can, and if you are curious about the water level simulation, you can collect the data of cross-section data and give river cross-section data as an input to hydrological model. So basically this model, if you have rainfall and the topography data, you can simulate the discharge, river discharge, water level, and inundation river flooding, Banzil or inland flooding with a given parameter. So the basic concept of the model is that this is a two-dimensional model which is capable of simulating both runoff from the mountainous side to urban area or flat area, and flood inundation from river to floodplain. Or sometimes if you have heavy rainfall and that water is excess too much to drain to the river, there is inland flood happen, and this model can also simulate it. And this model divides a so-called river basin into several grids as shown in this figure. So the spatial resolution can be few meter, from few meter to 1 kilometer scale, depending on your interest of the analysis. Sorry. This slide shows the feature of the RRI model. So it can be, so I heard that Indonesia has a very fine topography data called DEMNAS, which is spatial resolution is 8 meter. But if you don't have topography data of your interest of area, you can use the satellite topography data and run this RRI model. You can run this model with typically with your laptop. You don't need a very high spec PC with a high spec, you can run this model with your laptop. And you can also choose some, hydrological processes in this area. So maybe in a river basin, there's urban area, or steep area, flat area, hydrological processes might be different. In RRI model, you can select the hydrological process as you, depending on land use, topography, or urban setting, and so on. And this model can be used for real-time, not only climate change impact assessment, but also for real-time application. If you want to do real-time flood forecasting, you can run this model with by giving the rainfall input at some time, or you can use this model to assess disaster. After disaster, you can use this model how the heavy rainfall impacted to specific river basin. You can also use this model for emergency response. So typically, I don't know, I heard that in Indonesia, you may use one-dimensional river routing models such as HECLAS or so on, or MIC-C. Typically, the two models are inundation. You need three components. First is a rainfall runoff model. This model can simulate the runoff from mountain to the flat area with given rainfall input. And the another model is river modeling. This model can simulate the river discharge or water level with given runoff input. And then finally, you need third model, flood inundation model. This flood inundation model needs some input from the overtop water or dike levee break. And so you need three models to model rainfall, runoff, and flood inundation typically. But this model can be, it's capable of simulating all at once, from rainfall, runoff to flood inundation. Especially this model is suitable for large flooding, where there is not so much levee. And next, so we would like to share our experience of RRI model, application of our RRI model to Indonesian cases. As Eva Sensei explained, as long as we don't know so much about the hydrological process or runoff process in Indonesia actually. So, for example, based on the knowledge in Japan, in mountainous area, quick subsurface flow can happen. Like if heavy rainfall happens, rainfall go to the soil, and quick subsurface flow can happen. And it is said that this quick subsurface flow in the soil will form the river discharge in the river. And then in urban area or paddy area, it's very flat area. If imagine that heavy rainfall happens, so most of the water, because the topography is very mild, most of the water doesn't go flow to the river, but it can form a ponding, or it can be just stored in the soil. So in this case, in the flat area, you can, based on the Japanese knowledge from the Japanese case study, you can use a vertical infiltration flow model. RRI model is based on the observational knowledge in Japan. The runoff generation can be consists of subsurface flow, quick subsurface flow in mountain, vertical infiltration flow in flat area. But we don't really know if this can be applicable to Indonesia. On the other hand, I will introduce our observation results from our observation sites. But we found out that in Indonesia, there is very thick soil. In Japan, the soil is less than 1 meter. if you dig the soil, you can easily find the very hard soil below 50 centimeter or 75 centimeter from surface. But when we visited Sumatra and dig soil, we can dig soil forever actually. We can reach 3 meter, 4 meter, 5 meter without any difficulties. So we were curious how the hydrological process in Indonesia and if this model structure can be applicable. So we assume that in Indonesia, because of thick soil, the soil can store very much of water, and we assume that there is a lot of groundwater. Groundwater process is more important than quick subsurface flow in Japan. So we are assuming this groundwater model. We apply this groundwater model to a river basin, and we compare how this different structure gives a result of the discharge in the simulation. So this is the result of the field survey at the Skantin site. Skantin site is located in the upland of Batanghar River Basin, the central part of the Sumatra. This is Professor Sayama. His height is 180 centimeter. So you know how the soil is thick, it's about 2 meter. So based on our field survey, we recognize that this soil depth can be up to 4.5 meter or at the downslope near the river and 1.5 meters the upslope of the hill slope. So we recognize the importance of consideration of the thick soil in this area. So at the Skantin, actually it's near the Skantin village, so we call it Skantin site. At this Skantin, we have a groundwater monitoring, soil moisture monitoring, and we also investigated some soil, and we collect the soil and analyze the soil sample for the physical parameter. Based on the groundwater monitoring, we found out that there's very quick response. This is the rainfall, and this is the groundwater at different depths. As you can see, this rainfall is 40 millimeter per hour, and groundwater 3 meter below the surface can reach to the surface if this rainfall can happen. So based on this monitoring, we recognize the quick response of shallow groundwater at this hill slope. This one is the result of infiltration. We conducted the infiltration test at the forest palm plantation and tried to understand how land use change, how different land cover land use impact on hydrological processes. And we recognize that in the forest, the infiltration rate is, but horizontal axis is time, and we give the water to the instrument. As the instrument is saturated, we can get the saturated hydraulic conductivity. And we recognize that at the end of this experiment, forest has 300 millimeter per hour. So even though rainfall, which is 300 millimeter per hour, which can cause a flood, can happen, the soil can store all the rainfall. And then we recognize that palm plantation, although it's compacted or it's disturbed by human beings, it has 36 millimeter per hour. And 36 millimeter per hour is also high intense rainfall. And we recognize that even though the forest and palm plantation, regardless of the land cover changes, the soil has very high infiltration. So we assume that most of the rainfall can be in the soil and form the groundwater and cause the quick runoff processes. So based on, as I experienced, as I explained, different runoff processes are called, different runoff mechanisms can cause a different flood responses. For example, this is a dry condition. Once it in dry condition, if soil is dense, once it rains, the water can less water is infiltrated, but more overrun flow happens. But if soil is saturated, if soil has poor spaces, rainfall can infiltrate in the soil. And once it's saturated, overrun flow happens, but otherwise water flow in the soil. So we are curious about how so we did we set up some model and we tested different model structure and different soil parameter, and then see how those changes are influenced to the simulation results. In this case, we use a satellite rainfall map produced by JAXA in Japan called GSMAP Analysis version 6. This is satellite data collected by the gauge rainfall in Indonesia. And we also estimated the potential evapotranspiration by Penman-Montes with global data of the atmospheric data. And then we use the satellite topography data and globally available land use data. And because we are curious, typically Japanese soil is 1 meter, but in Indonesia we found out that average 3 meters. So how this 1 meter and 3 meter give different to discharge. And we measure some river depths and widths at 8 points of the Batanghari River basin and estimate the parameter of the river depths and equation to estimate river depths and widths. So we are curious that how the satellite rainfall can be used or correct or not. And I compare the satellite rainfall with the gauge data, and this figure shows the annual rainfall map, and this basin map shows the satellite, and this point shows the annual rainfall based on gauge. And warmer color shows the smaller rain, and the blue color shows more rainfall. And you can see that the spatial pattern of the gauge and the satellite are almost similar. And if you estimate the basin average rainfall in average, we got a similar number. And we confirm that this satellite rainfall is comparable with observation. And we plot the monthly average rainfall. Blue one shows the monthly average rainfall by satellite, and black one shows based on gauge rainfall data. We found out that satellite rainfall data is not so bad to represent the monthly rainfall. And red one shows the potential evapotranspiration, and it's constantly, the value is constantly between 100 to 150 millimeter, and based on literature, it's within the range of acceptable. In tropical region, the annual actual evapotranspiration is between 1,450 and 1,750, and our estimation is 1,500. So we thought that our evapotranspiration data based on equation and global data are not so bad. So we give this satellite rainfall and evapotranspiration data to hydrological model and make 4 case studies. And case 1 is a typical, case 1 consider only typical, case 1 is a simulation setting of the typical simulation setting in Japan. So no deep soil, no evapotranspiration, no groundwater. And case 2 considers the potential evapotranspiration data. Case 3 considers both deep soil and potential evapotranspiration data. Case 4 considers all the characteristics we found from the plot scale. And red one shows the observation, daily discharge, and blue one shows the simulation data. We found out that as much as we consider the deep soil, potential evapotranspiration rate, and groundwater flow, the simulation accuracy, model accuracy getting better. So we found out that based on this result, we found out that it's important to consider the hydrological processes found at the pro scale and consider in this basin model. This slide shows the validation of monthly discharge from 2001 to 2013 at this point. Black one shows the observation, and orange one shows the simulation. And you can see that there is not so much differences. And this is satellite, and two figures below shows the inundation map, and left one shows the satellite observation by Sentinel. It's freely available. And right one shows the simulated result. Satellite includes some noises, but as you compare both satellite and simulation data, you can see that simulated inundation map is not so bad. So using this model, we reflected some infiltration rate based on the land use change and then present rainfall and future rainfall to the model and see how the inundation is changes. So this map shows land use change impact and climate change impact. And vertical two figure, this figure shows inundation map based on present rainfall and present land use. And this one shows present land use and future rainfall. You can see that in the lowland or along the river, the inundation are expanding and depths are getting bigger. And then right top figure shows inundation considering future land use and future rainfall. If you compare both two, you don't see so much difference. So we found out that in this area, climate change can give more impact to the flood inundation. You may be familiar to SWOT model. SWOT model is a hydrological model that is developed for agriculture purposes or impact assessment of land use changes. We compare the future change of the discharge of RRI model and SWOT model with the same rainfall, future and present rainfall input. We found out that RRI model give not so bad about RRI model is not so bad about the land use change impact results. So this is our experience so far. So in short summary, we found out that the RRI model works well with by considering the unique characteristic of the scanting site. It can reproduce monthly discharge in the long term for 10 years and inundation depth. Dr. Eva will expand this talk about advanced RRI model and flood and fire in the latter part.
Thank you, Kodai Sensei. So let me continue this talk. So the previous RRI model explained by Yamamoto Sensei was the default RRI setup that you can download currently through the internet. And the next part that I'm going to explain is the advanced one that was recently developed by Sayama Sensei and Sugawara-san. And we found out that this advanced model may have a potential to be used to address both floods and fire due to the availability of soil moisture content in the simulation results. So we think that maybe RRI model can be also applicable to address future changes we can have like an integrated approach for floods and fire simultaneously in the future. So so the idea is to use flood inundation extent as it is as default RRI model, but we can use soil moisture using fire index to understand the fire risk, the future fire risk, and then we can make a kind of simple fire model so that we can have a simultaneous fire flood results in the future. So the advanced RRI model that was developed recently by just last year by Sugawara and Sayama includes the unsaturated flow, and the benefit, the merit of this model is that it can be applied directly using the soil parameters that we can obtain easily in the soil laboratory. So we don't really need to understand whether or not the runoff processes is applicable, whether we set the correct parameter setting in the default RRI model, but we can use the laboratory results in this model directly and we can have a confidence in obtaining the physical processes based on these parameters. So at first we try to make a simulation at a hill slope scale based on our observation in the Sekancing, and we made 2 monitoring sites. One monitoring is oil palm plantation site, and another one is in the forest site. And it does have a little bit different in topography. So in forest site we have like steeper topography, while in the oil palm site it has a milder topography. And we would like to understand whether or not this model can be used to explain the land use change impact at hill slope scale. And we have an observed groundwater level in this area. In this first row is the groundwater level at the forested plot. And as we can see that the groundwater level dynamically increase and drop immediately just after the rainfall. And we can see at the bottom part is the oil palm site. We can see the groundwater level increase and drop mildly after the rain. So we can see complete different groundwater dynamics in these both sites. And we wonder if this is caused by by land use change. So using RRI model, we try to switch. So we assume that the hydrologic conductivity, the soil water retention curve properties change due to land use change, or for example, if when forest is cut down, then many people say that hydraulic conductivity decreased, and then the soil water retention curve change. And we would like to know what is the impact of those parameters, and whether or not if we switch the parameters of those two sites, whether we can have a similar groundwater response. So in the first row, this is one of the results obtained by our PhD student, Elif Sang. He's working for Tangerang City Government. And in his results, we can see here the control simulation is the red one. And if we change this one is the forested site, so we can see that it's more dynamic than the simulation in the oil palm site. But if we change this forested site using the hydraulic conductivity of the forest, we can see that of the oil palm, we can see that the groundwater increased up to the surface. And if we change the soil water retention curve, actually it doesn't really change much. But if we change the soil depth of the forested soil similar to the oil palm, then the groundwater will decrease, and the pattern will be milder. On the other hand, in the oil palm side, we can see that this happen in the with the very deep soil. In the oil palm side, we have 8-meter depth, and we can see that the groundwater pattern doesn't really change much in this oil palm side. So based on this finding, we finally understand that we cannot really explain the land use change just by changing the parameters of the model, while we finally, the students finally now expand by using actual evapotranspiration rate difference between oil palm and forest, and he finally can find the land use change impact by the difference of evapotranspiration. So in this case, we finally realized that the geological setting and the soil parameters may have a higher influence to the groundwater dynamics compared to the just land cover change. So we realized based on this experience that the importance of soil characteristics in the hydrogeological simulation. So with our counterpart, it's called Apip Sang. He is from BRIN, Lipilimnology, and we took 91 soil samples in all Batanghari River basins, and to understand the hydraulic conductivity, porosity, soil texture, and soil water retention curve. And we want to understand the characteristic of these parameters compared to the temperate region. So we find out that in this region, actually the soil has much higher value compared to the value of the temperate region, explained here by these tiny black dots. And so therefore it's important with the advance of RRI model, we can finally make a simulation based on the soil parameters and not just calibrated parameters. As well as porosity, you can see that the porosity in humitropics is much higher than porosity in the temperate region, as well as the soil water retention curves. We can see that this lambda porosity distribution is much larger in humitropics compared to a temperate region. So we made a basin scale simulation in this case and compare when we used soil parameter in humitropics region and default temperate region, and to see whether or not the model can actually explain or make a difference in the simulation, and whether or not the simulation is improved. So this is the result. So the red one is observation, and the green part is simulation using temperate soil, and the blue part is simulation using observed parameter. And we can see here that it's still hard to follow the observed parameter. We still can improve the model simulation, but we can see that in the temperate soil, particularly in the low flow, the temperate soil cannot really have a base flow as much as the humitropic soil. So in humitropic soil, as mentioned by Yamamoto sensei, we can have much more groundwater flow, and so that we can have a base flow more than temperate soil. And we also see the distribution of soil storage, compared to default parameters, the measured parameters have a much more realistic distribution and not a kind of conspicuously different between soil types as in default parameters. So we think that this advanced RRI model it can be potential, needs to be improved yet, but its potential to be used for fire risk assessment for future projection. And we also use the groundwater module in this case. Maybe some of you want to also use groundwater module. It's very good to be used in Indonesia, but I think it's not really included in the RRI module. So if you want to ask how to use the groundwater module, maybe you can ask me or Yamamoto Sensei later on. So using the groundwater module, the simulation improved significantly. So next part is the climate change impact study that we use, and this part will be explained by Yamamoto Sensei.
So hello again. So I'm afraid that our talk is very long, but I heard that usually students here take 3 hours in one class. Is that correct? 90 minutes? Oh, so maybe you can still stand the time of our talk. So, but yeah. If you want to relax, you can be like this, or you can excuse for a few minutes. But I'd like to talk about the climate change impact study in the Batanghari River Basin. So maybe some of them are assessing the climate change impact to flood or coastal region as a bachelor study or master study or PhD study here as a researcher. And as Professor Mori introduced, in Japan has a big climate change project called the Sentan project, and the Meteorological Research Institute in Japan are very collaborative. It's very understanding and collaborative against climate change data in Southeast Asia. So in that project, they, talking about the climate model data, there is global model data from the CMIP 5 or CMIP 6. Spatial resolution is few hundred kilometer to 100 kilometer, and it's sometimes too coarse to give input to hydrological simulation. And as you may know, there is a dynamical downscaling group in the world called the CODEX group. They dynamically downscale the global climate data to 25 kilometers in Southeast Asia. But still, sometimes compared with the satellite rainfall, the spatial resolution are not enough, may not be enough. And in this sense, it's called in this Japanese climate change project, the Meteorological Research Institute in Japan, dynamically downscales the 20 kilometer global data to 5 kilometer over the Batanghari River Basin. And we use present rainfall and future rainfall input with a resolution of 5 kilometer as an input to RRI model, and see how much the future rainfall give impact to the flood inundation. And to downscale, we use the highest emission scenario called RCP 8.5 scenario. And as you can see, this is a maximum inundation distribution in 20 years in Batanghari River Basin in present climate. After and to use the rainfall input, we compare the rainfall input from the model with the satellite observation, and we found out that the model has a bias. So we correct the bias and give a bias corrected rainfall to hydrological simulation. So yeah, and this slide shows a flood inundation map based on the present rainfall and future rainfall. And as you can see that in the future, because of rainfall is intense more, and the rainfall duration is longer, the flood inundation along the river and in lowland area are much severe compared to the present climate cases. And this shows this figure shows the total inundation volume over the basin, and gray one shows the present climate case, and red one shows the future climate case with present. Blue one shows the future climate cases but no land use change, and red one shows the future climate and future land use change cases. And we recognize that inundation volume changed very significantly from present climate condition to future climate condition. But if you compare the different land use changes under the same future climate scenario, and land use can increase slightly inundation volume, and but we recognize that the climate change can give more significant impact to the change of inundation volume in this area. As Professor Mori said, we try to change assessment not only for hazard but also risk assessment. And in this case, we're curious about oil palm plantation. And from the Indonesian research government oil palm association called GAPUKI, I heard that oil palm is very important economic product in this Indonesia, and we are curious how the flood hazard is influencing the oil palm plantation in the future. And so we make the two scenario to predict the future land use of the oil palm plantation. One is business as usual scenario. This figure shows the total area of the oil palm plantation in river basin, and that one shows a business as usual scenario. We assume that the area will expand up to 2050 in Batanghari River Basin, following the business as usual, because oil palm demand of oil palm is still increasing, and we assume that. But based on the literature review, population in this region will be constant after 2050, and the demand will be stable. And so in this business as usual scenario, we assume the total area will be constant from 2050 to 2100. On the other hand, we make a sustainable path scenario. So we assume that agricultural technology will be much improved. So you need less area of oil palm to get the higher yield. So in this scenario, oil palm area can increase from 2050 to 2020, but since the agricultural technology or such as fertilizer or machinery or so on can be improved in the future, area is less area. The less area, we can get the higher yield with little area of the land. So in sustainable paths, we found out that oil palm area is not so area. We don't need so much land to get the high yield until 2100. But this is the total area of the oil palm plantation. But of the oil palm plantation, so we use a freely available open source land use model called CRU model. This is originally developed by the Dutch in the European countries, but you can see the application to many countries in the world. So the basic concept of the model is that you can give the land use demand, such as area, how much agriculture area, to the model, and you can give the suitability index at each grid. such as the oil palm, such as soil types or elevation or distance from river or housing distance to oil palm companies or so on. And then since we have two inputs of the oil palm area for business as usual and sustainable pathways, we give two inputs to this land use model and get the special pattern of the future oil palm plantation under different two economic scenarios. And this is the result of the 2,100 land use changes. Upper figure shows the current land use changes estimated based on the satellite. And the red one shows the oil palm, and green one shows the forest. And this is a protected area, so the forest, and we give the assumption of the model that this area is protected area, natural park, so it doesn't change in the future. It doesn't reduce in the future. Red one shows the oil palm area. This pink shows the open area, shrub and open area. So it's unused abandoned land. We found out that in sustainable pathway, oil palm area reduced, but shrub and upland are increasing in the lowland area. 5 more minutes. Okay. On the other hand, in business as usual scenario, oil palm are increasing over the basin. And if you focus on the lowland area, the oil palm area is increasing as well as the shrub and open land. So if we overlap the hazard of the present climate shown by the blue area and land use map, you can see that for the future, you can see the overlapped area between flood and oil palm in the this is a business as usual scenario. If the oil palm is produced as nowadays and flood is increases, the lowland area oil palm companies will face some more severe flood risk. On the other hand, if you take the sustainable pathways, the oil palm, you don't need land to produce the oil palm. So even though flood happens, you have less flood damage in the lowland area. And black area is a peatland area. So in sustainable area, you can have less oil palm in peatland area. And if you manage very properly the peatland area, it's going to be beneficial to the ecosystem management as well. So next.
So I won't talk too much because we have too much. So I just want to tell you just slightly about the fire risk assessment. So we also have cooperation with BRG in this case, and to understand which index is suitable, and we compare indexes in this region and use the indexes to understand the future fire risk. So this is based on SMIP 5 MRI CGCM. We can see that the fire area in the future will increase about from 42,000 kilometers to about 3 times in RCP 8.5, and also the frequency of fire will increase in the future from once in 1 decade into 8 times in 1 decade based on this MRI CGCM 3 data set. So that is and we also estimate the change in how the rainfall pattern and also the temperature actually change. We would like to understand the mechanism of the fire between, and we see. So if you have curiosity about this result, please ask me directly. Yes, I think that's all for today. Thank you very much.
Thank you very much, Eva Yamamoto Sensei, and Kodai. I'm so sorry. Kodai Yamamoto Sensei. Thank you so much. It's actually a really deep, heavy research from both Dr. Yamamoto's or Yamamoto Sensei. Any questions? Maybe we open for 2 questions first. Any questions from the audience? But I think for your research, it's show that the climate change definitely worsen the flood, worsen the fire risk. Is it in all Indonesia area, do you think? Because of those, I try to understand the soil characteristic for the tropical soil is different. So do you think it will apply to all Indonesian, all over the world, or what's the difference?
So, let me first explain about fire. So, fire will occur mostly more frequently. So, fire, because of the temperature change, most of the area will experience fire. In this present value, the northern part still not experience fire, but with the increase of the temperature, even the northern part will experience fire at least once in a decade. So, but with the change in rainfall pattern, actually, and also the change in temperature, actually, most severe part that experience fire will be the southern part, especially Palangkaraya area. Those that mega rice project will experience more fire, and also Palembang will also experience more fire.
All right, thank you. Any question? Any more question? No more? No question? Okay, please. Thank you.
Hello, my name is Jeremia Siombing. I'm curious whether there are so many global climate models in IPCC. How do we decide which one the best suitable model for our hydraulic model?
Question. You are asking, what's the best GCM to consider your simulation, right? Basically, there's no best global circulation model. That's a golden rule. There's a better model depending on your curiosity. Usually, we combine a few typical global circulation model for the assessment. What the typical means? It depends. If you want to estimate uncertainty range, you have to choose carefully typical one, because if you pick up very similar global circulation model, you can get a similar result, right? So you have to distribute the selection of the GCM depend on the target. That's the point. And then basically we believe classic global circulation modeler or institution more than newcomer. Then if you check the IPCC AR6, and usually we use more than 15 or 20 projection with weighted average. So nowadays we check the performance of the model to the historical observation and put the weight. And if model can, agree with the historical data set, we put the more higher weight. And if performance is low, we put a more lower weight. That's a typical thing. So you cannot select one or two few model. You have to select at least 5. And usually we select over 10 or 20.
Wow, 10 to 20 models. That's the not easy task, of course. Any more question? If not, maybe we could finish or we could close our discussion series today. Again, one more time, thank you so much for Mori Sensei, Eva Yamamoto Sensei, and Kudoi Yamamoto Sensei. Another big round of applause for our speakers. Thank you so much. Before we really close our discussion, I would like to ask Pak Adi, probably you have 1 or 2 words to say. Yes, please. Okay, maybe you can give some. Yeah, you could.
Okay.
Yeah,
Yeah, I have asked by Dr. Farid to close this event. So today, general lecture is collaboration event between ITB and PUPR. So I'd like to express my many thanks to all speakers, Professor Mori, Dr. Eva, and Dr. Kodai, for your nice presentation and share your knowledge and also share your experience. So I think today's lecture is very meaningful and fruitful for us. And also I'd like to thank you to everyone who actively participate in this discussion in here and also on YouTube. Yeah, we live streaming on YouTube, so we can't. Okay, so thank you very much again. Thank you for your attendance and participation, and see you in the next event. Selamat sore. Oh iya, mungkin kita foto sama-sama ya. Boleh. Silakan ke depan semua.